this video, we're going to look at how to use exact equations to solve first-order ODEs. Now, we like solving first-order ODEs because it makes us happy, and we also like knowing the theory behind it, because when you know the theory behind something, you can know it for real. So here's our basic strategy. So this video is basically just going to go through the theory behind the strategy. A subsequent video will go through actual examples. So if you just want the theory, this is the theory. If you want to see actual examples, that's the next one. You should watch both those, so it'll help you learn. So the strategy is that we want to write the differential equation as m dx plus n dy is equal to 0. Now this is important to actually go through the strategy, as I'm going to say, because if you just look at the final solution by itself, you're going to look at it and go, that makes absolutely no sense. Where'd you get that? I wish I had a theory. And then, woo, there's this video, so you can get the theory. So m and n are both going to be functions of x and y. So there you go. Now, so we're going to say that we don't know the answer, but we are going to guess. So, or not really guess, we're going to say, suppose there is a solution. So the idea is, supposing there is a solution, what would that solution look like? We'll call the solution F, capital F. Okay, so, yay! So we're going to call the solution capital F. Now, we're going to define df, well, not really define df, but it's true, if you know anything about partial derivatives, that the df is defined as partial f partial x dx plus partial f partial y dy. Now, if you don't know what a partial derivative is, that's what these are right here, is a partial derivative. If you don't know what a partial derivative is, that's something else that you're going to need to go look up on the side, but we're going to assume that you can take a partial derivative relatively, confidently here. So there you go. So say we've got this partial derivative that we're going to take. What we want to do is we want to match this up. So we're going to match it to our original, which is 0 is equal to m dx plus n dy. So clearly, I'm going to say clearly, because that's what all grad students say whenever they have absolutely no idea what they're talking about. Clearly, that means that df has to be 0, that m has to be partial f partial x, and n has to be partial f partial y. Of course, because, of course. Now, we know from calculus, according to calculus, the calculus monster, according to the calculus monster, if f is continuous, or has continuous derivatives, which is important to our assumptions, because we can't really have diffy q's if we don't have continuous derivatives at some point, then that means that if I take the partial of, basically the idea is if I do this, if I do the partial with respect to x and then the partial with respect to y, then it has to be the same thing as if I do the partial with respect to y and the partial with respect to x. I think I said it backwards, but I wrote it one way or the other. But I think you get the point, is it shouldn't matter which direction I do the derivative in. If I do the same kind of derivative in just a different order, I should still get the same final answer. So we're actually going to depend on that. So if I know that if I know that m is equal to df dx, if I partial f partial x, if I partial y both sides, then I'll get that partial m partial y is equal to partial squared f partial y partial x. Okay? Now if I do the same thing over here, I know that n is equal to partial f partial y. So if I partial x both sides, then I get that partial n partial x, can't spell, partial n partial x is equal to partial squared f dx dy, partial x partial y. Now, like I said, according to the calculus monster, if f has continuous, why is it a monster? It should be something more pleasant, but I think it's just because of the time of day that it has to be a monster. So, like I said, according to the calculus monster, these two things have to be the same. So the only way that any of our theory holds up, so our theory is only good if those two are equal. So the first thing that we have to do is we have to show that if we had actual numbers, that partial m partial y was equal to partial n partial x. If that's true, then we're good to go. Which means, when I say that we're good to go, then that means that f, the thing that we supposed exists, actually exists. And if something that we suppose exists actually exists, then that means that we can be happy. Because apparently we fought off the calculus monster. Okay. So, basically, so here's our strategy. Given m dx plus n dy equals 0, we want to check if partial m partial y is equal to partial n partial x. If so, we're going to solve it for f. So the way that we're going to solve for f is we're use either one, that we know that m is equal to df dx, and we know that n is equal to df dy. So using either definition, we could integrate both sides and get to f. So whichever one we use, so let's just pretend, yeah. Well, this is where it kind of gets hard to go much any further into the theory without actually using an example, so we'll go for an example. But basically, we're going to use either one. We're going to solve for f, and then we'll use the other one to kind of confirm and get any leftover parts of the function that we might be missing. And then we're going to use that to get our answer. So this is really just a derivation, because if I just said, okay, the first thing we're going to do is check this, you'd be like, where'd that come from? Why is this? This doesn't make any sense. So I just kind of wanted to show you through it so that later when we're actually solving these for real, you can get it. Oh, something I did mean to mention is that we had the df, or df itself. This was way up here. Where did it go? df is equal to 0. So if I integrate both sides here, f is a constant. That's a trivial solution. So sure, we could say that f is a constant. It's just equal to a constant on its own, but that's not really going to solve the problem for us, so that's why we're having to go the other direction. We will come back and use that in a very simple kind of way. But from here on out, now you've at least seen the theory behind the strategy for exact equation. Now, if this check comes out, if not, now we have to try another method. This method is only going to work for exact equations. So if this doesn't work, you have to try another method.